So it's my great pleasure to introduce Brendan Buller for this week's joint JHU Space Telescope Science Institute Colloquium. Brendan earned his PhD in 2013 from the University of Hawaii, working with Mike Liu, and his dissertation was recognized with the Astronomical Society of the Pacific's Trumpler Award for Best Dissertation. He followed that up with prize postdoctoral fellowships at Caltech and UT Austin, and then a Hubble Fellowship at UT Austin. He was on the faculty at UT Austin for a few years before recently moving to UC Santa Barbara, where he's currently an associate professor. Brendan's also been recognized with the Sloan Research Fellowship, and he has, for the last several years, been doing very, very interesting things in direct imaging, astrometry, and the understanding of what it is these wide separation, several Jupiter mass things might be. And so today, he's going to tell us what he and his junior colleagues have been working on these last few years.
Thanks, Kevin, for that very nice introduction. It's really nice to be back, and I've had a lot of wonderful conversations with many of you today. I was trying to think about the last time I've been back giving a talk at Space Telescope, and I think it was 2016 at a Hubble Symposium. And so I've been here since then, but I have not had a chance to talk to you here. So it's really nice to be back. I wanted to start off here with this beautiful disk. The premise of this talk is going to be primarily about giant planets and what we've learned, a little bit about the life and times of giant planets, and hopefully the beginning of maybe a synthesis of giant planets across space and across time. But I love this disk. This is HD 169142. This is taken with ALMA. And every feature, there's of course some noise pattern and structure in the background, but every feature here is real. These annuli, these gaps, the azimuthal brightness asymmetries, the brightness here at the center, some of the wakes, some of the regions within the gap, within this this thin ring that are absent of flux. And in particular, not only is it aesthetically beautiful, but it speaks to the, in my mind, to the interesting dynamics of what are presumably planets, probably lower mass planets at wide separations. And the point is driven home with this scale bar in the lower right. 10 AU is this size, and most of what we see, most of what we think about, most of what we see on archive, right, every day, is really isolated to this beam size here within a few AU, and in particular within 1 AU. And so this is just a reminder that there's a wealth of information and dynamics and formation and migration that occurs at much wider separations. And so I'll speak a little bit about this outside-in direction and how we're merging with closer separations over time. I think one of the themes that has been that has really emerged over the past 15 years, especially over the past 10 years, is simply the diversity of protoplanetary disk structures and features. We still don't quite know the taxonomy of how this all plays out, and there are, of course, many biases associated with large and bright disks. But there's clearly a lot of exciting behavior and dynamics and groupings that we can begin to cluster these disks under. And so, for instance, the near-infrared scattered light disk features that are being identified with GPI and polarimetry and sphere. This traces small grains in typically the atmospheres of disks. So we're probing a different layer and a different grain size than, for instance, in the submillimeter, which samples disks at that scale of millimeter, submillimeter wavelengths. The diversity can be, in some ways, mapped to dust mass here and stellar mass, and there are some correlations that are beginning to emerge. The protoplanetary disk mass scales with a large degree of scatter, but in general scales with stellar host mass and also with age. So not only are the relations like this, but they descend over time as you clump these groups of nearby star-forming regions by age. But the scatter is enormous, right? This is a logarithmic scale, so we have 3 orders of magnitude in disk mass. There's also interesting correlations that are emerging as a function of size. So on the y-axis here, we have disk size, which is distinct from the gas disk size. It's typically smaller because of a radial migration process that occurs. But for all of the large disks that are beyond, say, 30 AU in extent, they all seem to be structured, and quite literally all. This recent paper, when biases associated with edge-on disks are removed, the incidence of structure, of any kind of structure within the disk, is something like 98%. So all large, spatially extended disks appear to be structured. And yet many disks are compact. And the bottom line with all of this is this diversity in initial conditions ultimately gets mapped into the diversity of planets that descend from these initial conditions. So this is a plot we're all familiar with. We have mass and separation of the known planets with different techniques. Now, there's a huge degree of incompleteness associated with this plot. And with the transit method, for instance, the transit probability scales inversely with separation. The RV semi-amplitude scales as 1 over square root of r. So for a given mass, it's more challenging to find planets at wider separations. And with direct imaging, the bolometric luminosity of a planet scales with mass to the 2.5 power and inversely with time. So that means that more massive planets that are younger have higher luminosities and therefore higher fluxes. They're easier to find. So while imaging probes a larger spatial extent, we bottom out, right, in the giant planet regime. Nevertheless, we can start to stitch together some kind of picture of what planets are doing, giant planets in particular, even though we're still somewhat incomplete with direct imaging at wide separations. And so why are giant planets interesting? They dominate the mass budget of planetary systems. For the solar system, it's about 90% in total mass. Of the planets, it's about 90% of total rotational and angular momentum. Giant planet dynamics impacts all the other planets and the possibility of other planets residing in dynamically stable regions, and especially if they take on large eccentricities. So not only will they carve out some annulus, but that annulus will grow as the eccentricity of that planet grows. We think the giant planets are probably important for habitability and the delivery of water to what are otherwise dry inner terrestrial planets. We think Jupiter did this for our own Earth, and this may be the case in other systems, so there's a relevance to habitability. And they're simply the easiest things to find. The transit depth scales as the planet radius squared. The RV semi-amplitude scales as planet mass. The bolometric luminosity scales as mass to the 2.5. The contrast, both in thermal emission and in reflected light for a planet with direct imaging, scales as the size of the planet. And then the astrometric reflex motion scales as planet mass. And all this is to say that radii and masses matter. They scale as powers of 1 to a few. So giant planets are easier to find with all these methods. So we can begin to stitch these together and create, let's say, a quilt or a tapestry of what planets look like, at least across separation. And I think the goal, one of the goals in the field, something I'm excited about, is also doing this as a function of time. OK, so a couple of points I'll talk about are how and when do giant planets assemble? So what can we say about the assembly timescale and the evolution of circumplanetary disks? Where do they form? What are giant planet demographics like across 5 orders of magnitude in separation? How do planets dynamically evolve over time? Do they interact over time? Do they dynamically heat up, or are they basically stable on circular orbits over long periods of time? And then I'll talk a little bit about some of my hopes and maybe fears associated with the Gaia revolution that's about to happen. And if you're not familiar with this, I'll get this out there early. Within 10 months from now, the expectation value for the number of planets that will be discovered astrometrically will go from basically 0, or one could argue about a couple of them, to of order 10 to the 4. So certainly many thousands, and probably at the scale of something like 10,000 planet candidates. They need to be validated. There's a lot of work to be done. But this is a very exciting time for giant planet demographics. OK. So giant planets form from, this is planet mass here as a function of time. And this diagram attempts to synthesize a huge number of very complicated processes that I'm going to ignore right now. But let me just say, if we're looking at the giant planet regime, there are 2 dominant processes. There's an epoch of core formation that occurs on a time scale of probably at the level of a few mega years, 1 to 3 mega years, and then runaway gas accretion that happens faster. So the giant planet forms from a core that then accretes gas, and most of the mass is locked up in that gas. For other smaller planets, these typically form on longer time scales if, say, an ice giant or a mini Neptune accretes some gas, but not too much. If the gas disk dissipates before it has the opportunity to assemble into a more massive planet, it will be sort of stuck in this regime. And terrestrial planets probably form from a phase of giant impacts that can last a very long time. And this phase of oligarchic growth is such that the more massive failed cores will simply be left behind. So Earth, for instance, probably formed on a timescale of 50 to 100 million years, compared to Jupiter, which formed on the timescale of a few million years. So I think one of the interesting questions is, during this formation process of a young giant planet, is a growing planet, or are growing planets, are they comparable or analogous to accreting young stars? And if so, to what extent? So for a young star, it will form primarily from accretion of gas through the disk onto the photosphere of the star. And this occurs through typically magnetospheric accretion for young stars. Ionized gas will fall along funnel flows and will produce a shock onto the surface of the star. And this shock will tend to radiate UV wavelengths through recombination line emission. And then there'll be an excess at longer wavelengths from the warm disk itself. And so, at least in terms of the big picture qualitative similarities, the accretion physics, perhaps the disk structure, the central heating source, and also the possibility of the formation of planets for a young star or satellites for a circumplanetary disk are expected to be largely similar, qualitatively similar. But there also should be differences. So planets form within the circumstellar protoplanetary disks of young stars. And because of this, they form in an embedded phase. And so the expectation is that there will be vertical inflow, not just inflow through the equatorial disk. Tidal interactions with the host star will limit the size of a circumplanetary disk, typically to about 1/3 of a Hill radius. Gas replenishment will occur for protoplanetary disks, or circumplanetary disks, but not for protoplanetary disks. And in general, everything is scaled down. So we expect weaker shocks and perhaps no magnetic field or a weak magnetic field. This is basically unconstrained observationally. And if there's no magnetic field, then the disk might actually reach all the way to the surface, and another accretion mechanism called boundary layer accretion might dominate the accretion process instead of magnetospheric accretion. But every word there is associated with huge unknowns, and this is virtually untested. But this is some of the ideas that are being thought about. And so what do we see observationally? There's sort of two regimes. There's a regime of accretion and accretion signatures, which can emerge from these young planets, and a regime of thermal emission at longer wavelengths. So we have bound-free emission that can produce these continuum jumps, a Paschen jump, a Balmer jump, and then line transitions that produce emission lines. And in principle, these lines, if the accretion rate is high enough, will be brighter than the planet itself in thermal emission. And so these have been used, for instance, to look for young planets as basically lighthouses, right, where they might shine in H alpha or another emission line in a way that is easier to detect if you look here than in thermal emission from the photosphere. At longer wavelengths, we expect most of these disks to be relatively cold because they orbit a relatively low luminosity host. And they should be brightest at mid-infrared wavelengths, which of course is perfect for a facility like JWST. OK. So as an example of one of these circumplanetary disks, I want to highlight one system, SR12C. This is one of these nice case studies that is easy. So this is at a relaxed 9 arc seconds from its host star. The best mass estimate right now, and this is all assuming the cooling models that we use to infer masses are correct, but we think that they're more or less right. It should have a mass of about 13 Jupiter masses. It's in the Rho Ophiuchus star-forming region at about 140 parsecs. It doesn't actually have a Gaia parallax for the host star because the host is a binary. But we hope that a good solution will be in the Gaia DR4 catalog that's coming up soon. And the community has been able to assemble a broad wavelength SED for this planet. In fact, this is the broadest that I know of. It spans 0.2 microns out to 880 microns. So this point, and there are 3 regimes. There's an accretion regime at UV wavelengths, photospheric emission in the middle, and then the circumplanetary disk at long wavelengths. So this is a paper that my student Claire Finley just submitted last week. There's a known disk around this system. It was discovered or imaged for the first time by Yalin Wu in a paper from a few years ago. It's only the second planetary mass bound companion with an ALMA detection. And the ALMA detection is exciting because it's probing dust. And so it means that there's grains that are emitting. And it's unresolved. So the limit on the size of the disk is something like 5 AU. So we're already beginning to get some constraints. If we assume optically thin emission, which is the tradition in the field, then the expected mass of dust is about a lunar mass for this particular object. I'm co-leading a JWST program to image many of these wide planetary mass objects. You can see how straightforward the detection is for this particular object. This is MIRI imaging spanning 5 to 21 microns. And then we also have an HST program to go after the UV to red optical emission for the same systems. So already you can see this point here, the strong H alpha emission. This was known before, and we can actually compare this line strength to previous measurements. But this is new down in this regime, which samples this Balmer continuum jump. And the punchline of all of this is we can extract a lot of information. And so this is one case study, and I'll walk through some of the numerical values, but they're a little bit less important in general. It's more just to motivate this field. So for the photosphere, of course, we can learn about the physical properties, effective temperature, the surface gravity, the size, and through models, the mass. And there's some signs that there might be some substructure within this disk, so it's not well fit by a single black body and is best fit, at least statistically, with a two-component model. What I don't like is the fact that there's, most of the structure here is at a wavelength where we're not sensitive to. And so there are other models that have been fit the data pretty well, like an irradiated disk model. So I don't know about the substructure. I would add a question mark here at the end. But in principle, we can get from the scaling here, the size, the characteristic size of the emitting region, and the temperature. So at least for this inner component, something like 20 Jupiter radii and 500 Kelvin or so for a temperature. We can get the extinction from the blue, the UV through blue and up to red optical photometric points. And then most importantly perhaps, is the accretion rate. So fitting slab models, hydrogen slab models, hot hydrogen slab models, gives an accretion luminosity of something like -5. And then turning this into a mass accretion rate, we get something like 10 to the -11 solar masses per year. And just to put this into context, is it strong or not? We can, in an order of magnitude sense, compare the total mass of the system to its age to get a feeling for what this could have been like in the past. This is going to be dependent on formation mechanism. And so if this object formed like a star, like a distant binary, then perhaps most of the mass was already there, and we're just seeing the tail of accretion. If it formed from a core accretion-like scenario where most of the gas fell onto the planet, then we could at least get an average assessment here of the accretion rate. The result is something like 10 to the -9 solar masses per year, which is much greater than 10 to the -11. And so if it formed like a planet, which it may not have, but the past accretion rate would have been much higher. Either way, the bottom line is that this is at the end stages of assembly. Over the next one or few mega years, this 10 to the -11 number will add a negligible mass to the current mass of the object. So it's basically at the tail end. We're seeing this in what is probably a T-Tauri-like analog phase, or maybe a weak-lined T-Tauri star phase. The MIRI data also provide clues about what is going on within the disk and what the dust properties are like. So here's just an example of a silicate emission feature for a disk around an erupting star. This can change depending on the properties of the host star. These are grains that have descended from the ISM into the disk. And if they grow over time, then this strong emission and broad emission feature will dampen down, and you'll no longer see it if the grains are large enough. It will also settle into the midplane. And so the fact that we're seeing perhaps a suggestion at a few sigma, but the fact that it's not strong means that there must be some degree of grain growth occurring in the disk of this object. So this is perhaps the beginning, early days of exploring the growth of solids and perhaps even moon formation around a planet or a planet analog. And I'll just say that this is a coordinated effort, so that we have 2 papers coming out on this particular system. And then Kim Ward-Duong is leading a cycle 4, I believe, JWST program focusing on SR12C. And there's a lot of exciting results in terms of the gas phase and gas chemistry within this disk. OK. So if we look at this as an ensemble, we have SR12C. We can add in a few other exciting planets, PDS70, B, and C. For both of these, you can see the accretion rates are at a comparable level, 10 to the minus 11 solar masses per year. The masses and ages, at least in an order of magnitude sense, are all kind of comparable. This beautiful new Wispit 2b planet, 5 Jupiter masses at 5 mega years, beautifully nested here in a gap within this disk, 10 to the minus 11 solar masses per year. It's been detected in H alpha. There's all sorts of problems turning an H alpha flux into a believable accretion rate, but let's just imagine that we could do that. AB or B, which is a potential planet, let's say, at about 100 AU, also about 10 Jupiter masses, a few mega years. And if we believe all of this, these empirical connections between H alpha accretion line and bolometric accretion flux, or bolometric accretion, and transforming that into an accretion rate, we also get something similar here. So the punchline with all of this, the big picture, is that regardless of how these objects formed, we tend to call them protoplanets within the community. I would argue that they are not akin to protostars in a collapsing phase, but much more similar to T-Tauri stars at the tail end of the mass buildup and the growth phase. So I think most of the assembly is probably over for these objects. OK, so what are we saying about grain growth? So we have some hints, perhaps, that there's some silicate emission at 10 microns for this particular object. There's some beautiful work that was carried out here for a WISIS 1b with a nice infrared excess and silicate emission feature that was this in Nature, I think, earlier last year. There are a few more objects within our program that are starting to speak to the diversity of this silicate feature. So at 10 microns here, you can see an elevated peak for one of these objects, a higher one here, and perhaps no signs of emission for these other two objects. So I'm not saying a sample of 6 is statistically valid, but I think it's starting to paint perhaps a bit of a story of growth, and it will be very interesting eventually to assemble larger samples and look for evolution as a function of planet mass, as a function of age, and perhaps even environmental context, if a planet is close to its star or out at, say, 1,000 AU. OK, so how do we get more of these? It's been a challenge in the community to identify young accreting planets. I just wanted to highlight one result that came out recently from Gabriel Cunho and collaborators. This is work that was done in part with JWST and ground-based instruments. And it involves not a planet, but a background star. So we in the direct imaging community are intimately familiar with all these false positives. We get spooked. We get tricked all the time with these. So you find an interesting source, you think it's a planet, and then you wait a year or so and it's a background star. Now it turns out these background stars have some utility. Some of them do. In this case, this was a really, I think, creative example of using this background star to build an SED. And it happens to fall exactly within a gas gap here, a CO gas gap of the star AS209. This is one of these famous young disks with beautiful dust structure. The CO emission extends farther out, and you can see it falls within one of these lanes. And so this allows you to quantify the degree of extinction within the gap, really for the first time. And so they arrive at a value of something like 4.6. I think it's plus or minus 1 or so, the scale of the uncertainty. And all this is to say that it is very possible that planets are doing these carvings out of these rings and gaps, and we're just not seeing them because of considerable extinction. So we're starting to assemble a larger sample of these background stars with interesting disks. This is IM Loop, which might be familiar to some of you. And there are at least 2 things which I think are background. There's one here, and there are many more examples. But hopefully, eventually, we can quantify the impact and really the optical depth of these disks with a larger sample. Okay, I want to transition to what's been learned about the radial distribution function of giant planets. So this is an assembly, and there are caveats and biases and such, but it's really a first crack at kind of, and other folks have done this as well, but this is sort of an illustration of planet occurrence rate as a function of separation spanning 5 orders of magnitude. So it's been known for a long time that hot Jupiters and their warm Jupiter counterparts out to about an AU are relatively uncommon, about 1% for sun-like stars for hot Jupiters and a comparable occurrence rate, something like 1 or 2% for warm Jupiters. Of course, the first planet that was found around a sun-like star is 51 Peg, and this is one of these hot Jupiters, so about 1 in 100. As we march out to cold Jupiters, and every word there takes about many years and careers to get at, because it's very challenging to march out, especially towards 10 AU. But you need long baseline coverage, decades of coverage to march slowly out with the same experiments. It's sort of like these experiments that are carried out in biology to watch evolution in real time. They take decades and careers, and the torch is passed on. I see this effort as a similar kind of process in the field of exoplanets, starting in the 90s all the way through today from many independent groups. And one of the I think, exciting aspects in terms of demographics is that there's a commonality. The same trend is seen. Once you march out to about 1 AU or so, this is a little harder to see on this logarithmic plot, but you see it here on this linear plot with the California Legacy Survey program, the Anglo-Australian Planet Search, and then also the HARPS and Coralie search. There's a jump at about 1 AU and a general rise. The occurrence rates get fuzzier. There are fewer numbers the farther out you march, just because of the sample sizes and the duration of these programs. But this is sort of qualitatively what is being seen. There's a peak of cold Jupiters. This seems to be, these are all old stars, but it seems to be, if we think that we're seeing them where they formed, it's telling us something about the site of where giant planets form. So perhaps the giant planet production zone, 1 to 10 AU. With direct imaging, the occurrence rate seems to diminish as you go farther out to something like 5 to 10% from large direct imaging surveys with extreme AO instruments, out to perhaps 1% or so much farther out. So there's been a beautiful collage here of efforts from different teams internationally, and the haul is something like a few dozen image planets to date. Of course, JWST is opening up this landscape to lower masses and to older stars. Okay, but if you want one take-home number, you can add all these together, and you get something like 25%. So roughly 25% of sun-like stars harbor a giant planet from Saturn mass to about 15 Jupiter masses, from 0.1 to 1,000 AU. And more rigorous additions here, summations, get basically the same result, something like 20 to 30%. Okay, so what is this telling us about giant planet formation and evolution? The disk surface densities dramatically decay. So I showed that original plot with that beautiful 100 AU scale disk, but of course the disk surface densities decay by orders of magnitude across that spatial scale. So most of the stuff, most of the mass is close in, and that's where most of the action happens, most of where the planets form. But there's also a water ice line, which for sun-like stars is a few AU. And so what we perhaps are beginning to see here is this combination of both a lower disk surface density, the fact that time is slowed down as you go to wider separations, orbital periods are longer, and it takes more time to grow cores to then accrete gas. And then at smaller separations here, the water ice line, which is this transition where planetesimals, which incorporate water ice instead of simply rock, are more easily able to assemble and grow on a faster time scale. So this perhaps is a balancing act of those processes. But it's more complicated than that. I've spoken to core accretion here, but at wider separations, disk instability for particularly massive disks that go tomb ray unstable and collapse down in a top-down fashion, maybe happening in some cases at wider separations. We may also be seeing the mixture model of planets or planetary mass companions that have formed from the turbulent fragmentation process of star formation. In this case, these would be basically opacity-limited fragments that failed to accrete, and they're just left in the planetary regime, and they're essentially wide, high mass ratio binaries. And there's also the possibility of dynamical capture in these rich, dense clusters. A planet could be ejected and could be sort of ionized, and then could effectively be recaptured by another star. Then this is convolved with migration, right? So we have inward migration through different mechanisms, disk migration, planet scattering, high eccentricity migration with a third object, or outward scattering, or outward resonant migration. This is a really hard and challenging set of conditions and mechanisms that we're all trying to sort out. But we can marginalize over these details and at least show this first crack here at this radial distribution function. So I think overall we have a general sense, and the details still need to be worked out, and there's a lot of exciting effort there. But I think we have a general sense of where giant planets form. And what I'm really excited about is the time, the temporal dimension of how and when did they get there. Was this distribution function, this period distribution, was it sharp initially and then over time gradually broadened out? Were giant planets initially a little bit farther out and then on average moved in? There are a lot of unanswered questions about where they typically form and how they move around over time. So we can begin to look at that through at least one clue from the orbital architecture of planets, and that's with their eccentricities. So hot Jupiters are tidally circularized. So these are in some sense not entirely, but kind of useless. I shouldn't say that with this crowd. Don't quote me on that. Useless for, at least dynamically, except perhaps their spin orbit alignment or misalignment. There are important clues there. But because they're tidally circularized, they don't preserve the initial conditions of how they got there. So instead, if we march out to warm Jupiters, I have a graduate student, Marvin Morgan, who has spent the last several years assembling over 18,000 radial velocities, taking hundreds of new observations, and trying to pin down the eccentricities for a large sample of warm Jupiters between about 0.1 and 1 AU. And the advantage here is that at this separation, giant planets don't tidally interact, and so they're at least removed from that. They don't tidally circularize on timescales that correspond to kind of the stellar age of the sample. These are all field stars, so a few gigayears, and has a series of papers that focus on not just the fits, but the correlations, the underlying trends that are emerging. So first of all, the warm Jupiter eccentricity distribution is broad. And this has been known at some level beforehand, but he's quantified it precisely using the same homogeneous RV Keplerian fits, and found an occurrence rate of something like 73% of warm Jupiters which have non-zero eccentricities. So the first big picture answer is that warm Jupiters are dynamically excited. They're very distinct from, say, Jupiter in the solar system, which has a very mild eccentricity of a couple percent, 0.05 or so. And so Jupiter would maybe fall here. Most warm Jupiters are excited, dynamically excited. And there are also interesting trends that are emerging. So this particular result has been known. You can see this without doing any population level reconstruction of the underlying distribution. The blue points here are the metal poor host stars. The orange points are metal rich. And you can see that the distribution of eccentricities is broader for metal rich host stars, and it's narrower, it's more circular for metal poor host stars. So this is a well-known metallicity eccentricity correlation. Marvin is also now analyzing the dependence of stellar host mass by splitting the sample into different bins, and the multiplicity, so whether planet multiplicity and stellar multiplicity play any role in this, and then also evolutionary phase. So he has a couple more papers that he's working on and should be out later this year that speak to actually some really exciting correlations there. As we march a little bit farther out, there's a new result from Greg Gilbert that I don't have the citation here. Gilbert et al. 2026, which analyzed the eccentricities of cold Jupiters from the California Legacy Survey. The result is similar. There's a broad distribution of eccentricities, and interestingly, this scales with planet mass. So as you go to more massive giant planets all the way to brown dwarfs, the eccentricity distribution gets broader. So here's the flat distribution for brown dwarfs in this kind of 1 to 10 AU characteristic range. And then as you divide the sample into lower and lower mass bins, you get more and more circular orbits. So there's some dependence on planet mass that relates to either the excitation or the formation of these objects. At wider separations, I and a few other teams have looked into the eccentricities of directly imaged planets. And the results are qualitatively similar. There's at least a distinction of low eccentricities for imaged planets, and I've been talking to a few of you today, and it seems to be reinforced with larger numbers and greater, better precision on many of these eccentricities. And the brown dwarfs seem to have a broad eccentricity distribution. This is all between about 5 and 100 AU. So at least qualitatively at this level of resolution, there's a similarity here that's emerging. And that is that giant planets are less excited or less eccentric than brown dwarfs, and there seems to be a mass dependence to that. Okay, I want to switch gears and talk a little bit about stellar obliquity for a few minutes. So this is the angle between the orbit of a planet and the spin axis of the host star. And that's not to be confused with planetary obliquity, which is the orientation of the planet with respect to its orbital plane around the star. So there's a couple angular momentum vectors. Here I'm just focusing on the spin axis of the host star and the orbital plane of the planet. So here would be an example of an aligned system. We usually use psi for the true obliquity, and misaligned here. Now this is relevant because the solar system is misaligned. The sun has an obliquity of about 6 degrees with respect to the invariable plane, about 7 degrees with respect to the ecliptic. The invariable plane is this mean angular momentum vector for the entire solar system. So the sun is misaligned, and it's not clear why that is. There are a lot of ideas, creative ideas out there. Planet 9 may be torquing the sun over time, or a passing star could have disrupted either the coplanar solar system or perhaps the star. It's not, or it could be primordial. It hasn't really been clear. So we're not answering this, but I worked with a really talented postdoc, Lauren Biddle, who's at Princeton now, to think about the primordial stellar obliquity distribution. And the approach she used was to look at ALMA-resolved protoplanetary disks, which have really precise inclinations. This is sort of standard fare now to get these really precise measurements at the 10th of a degree level for extended resolved disks. And we could play a simple game. So it's easy, relatively easy to measure for non-heavily accreting stars, just kind of normal young stars that are rotationally broadened. We can measure a v sin I, and this is a projection of the equatorial rotational velocity. You just get a high-resolution spectrum. If you have an estimate of the stellar radius, and if you can infer a rotation period from, say, a light curve like TESS, then you can back out the inclination. Now, this is sort of a straightforward approach. There's a little bit of nuance with respect to correlation between v sin I and v equatorial, and that can be taken into account. But when we do that, so she did this for about 50 systems. Here's an example of one rotation period, and it's not as clean as it is for a nearby field star or a nearby young star, because accretion tends to disturb and produce variability. But overall, we kept the reliable ones. So when we play this game, we can back out an inclination. It's not the full answer here. We don't know the orientation. There's a spatial orientation that's related to the polar position angle. It's sort of a longitude of ascending node analog. But we can get a sense of at least the inclination with respect to the sky plane. We don't know that orientation. And so in this case, it's delta I, just subtracting one from the other, gives you a result that's consistent with alignment. And we could do it for other objects. Here's a disk that's at a 45-degree angle. Lauren measured the rotation period and inferred a stellar inclination that seems to be equator on. And so this, we would infer that there's a strong misalignment. So she did this for all of the available systems by carefully building catalogs and then applying filters. And we thought carefully about the biases that might be imposed in different directions and from different cuts. So this was a Nature paper she had last year. This is delta I on the y-axis and spectral type on the x-axis. All of the solid points here, these are the statistically misaligned systems. And the big picture result is that most systems are aligned. Most protoplanetary disks, which trace the outskirts, right? This is at about 100 AU. We're not talking at 1 AU. We don't have that spatial resolution. But at least at wide separations, the protoplanetary disk predominantly seems to be aligned. But about a third of sun-like stars harbor misaligned disks at the few tens of degree scale. And so if we put up the pre-main sequence sun, which had a spectral type of something like M0, it fits snugly in this distribution. It's not a particular outlier. 7 degrees doesn't seem to be an anomaly with respect to this larger sample. OK, so we're not saying it is necessarily primordial, but it's consistent with this primordial obliquity distribution. And so what is causing this? There's one of the mechanisms that I tend to like is this idea of late infall. So young stars form from the collapse of a dense molecular cloud core. And that will produce a star and a presumably aligned disk. But that's usually not the end of the story. Infall continues to happen over millions of years. We see many examples. Here's just one example from, this is SU Oort, a really distant 30,000 AU companion to AB or Gaia. And these streamers have been seen with better and better data. The surface brightness is relatively low, so they're hard to find. But this is just an instance of, we have a misaligned disk here, which you can see from this hamburger-like shadow. So there's an inner disk that's misaligned and shadowing the outer disk here. We have streamers happening here. There's a lot of stuff happening. And so it's perhaps not crazy to think about late infall as producing a source of differential angular momentum that is deposited onto the disk, and that differs from that of the main star, perhaps that formed 2 mega years before. So it's one idea. So we can start to think about this over time, and this was, I would say, pioneered. There are a few groups that did this before, but the largest sample was done by Meredith McGregor here and a student. She did this for debris disks. And so this was the same approach using resolved debris disks, same kind of spatial scale that's being probed, but a bit older than protoplanetary disks at the level of tens to hundreds of mega years. And what they found is that most systems, again, seem to be consistent with alignment. The 1-to-1 means aligned. And there are a few outliers that are kind of consistent with the same broad fractional occurrence rate of something like a third. So I've thought about this with some other collaborators for distant giant planets and brown dwarfs. These are a series of plots. I tried to call them boomerang plots because I like that name, because they look like these are stellar inclinations here. And there's a degeneracy in terms of whether it's pointed towards us or away from us. And so each one of these kind of traces out a different boomerang. It hasn't really picked up. That's OK. But we can play the same game of delta I and look at that distribution function for brown dwarfs and giant planets. And this was assembled into this nice plot by Aldo Sepulveda in a paper a few years ago. And this is and I saw an update from William Ballmer earlier today. It's strengthened, it's reinforced this trend. The giant planets whose host stars we can measure an inclination seem to be consistent with alignment. So they all fall on the one-to-one plot. So distant giant planets seem to be aligned. The brown dwarfs, on the other hand, have a lot more scatter. OK, so this is, I missed it. Could you pause the feed? So this is a plot that Lauren Biddle is including in a new paper she's about to submit. This is the delta I distribution assembling all of these samples. So the debris disks, the protoplanetary disks, and hot and warm Jupiters, which can be probed at smaller separations. And this is all the same methodology, same cuts, removing binary stars, same mass range, single sun-like stars. And the big picture as a function of age and as a function of orbital separation is that there's no clear difference, at least at face value, between the protoplanetary disk primordial obliquity distribution and the same kinds of measurements at wider separations here and at older ages. And so at least with the data in hand, there seems to be, let's say, a preservation of this initial distribution across space and time. You can see that there's a lack of intermediate age systems and intermediate separation systems. And I think Gaia DR4 is going to clean this up really nicely. OK, which brings me to Gaia DR4. OK, so Gaia is an astrometric mission that's measuring parallaxes and proper motions and all sorts of other stuff for about 2 billion stars. We are through the epoch of DR2 and DR3 here. Data release 4 is happening in 2026. There's a longer baseline. All of the individual epochs will be released, all the epoch data, so the individual astrometric measurements. And there will be a DR5. We don't know when, perhaps 2030 or so. So why do we like astrometry? It is basically insensitive to stellar age. And that's not entirely true, but it's pretty true. So we can find giant planets at young ages, intermediate ages, old ages. And we're not just limited to the techniques that impose all these age restrictions that we've historically had in the field. Planets can't hide from astrometry in the way that they can from radial velocities. So a face-on planet will produce no radial velocity signature. And with direct imaging, it'll bounce around from one side to the other. And it might just barely exit the contrast curve. But with astrometry, whether it's edge-on or it's face-on, we're seeing the tangential motion on the plane of the sky. And so as long as you're at the sensitivity where you could detect them, we should be able to find them. And so the orbits, masses, inclinations, and demographics of thousands of giant planets as a function of age, metallicity, host mass, multiplicity, planet multiplicity, all these parameters that I think are really key to understanding the narrative of giant planet formation and evolution, I think will eventually be unlocked with this kind of data set. The expectation value is of order 10 to the 4 giant planets in about 10 months. Now, the best predictions put it at a little bit less, but there will also be a comparable number of accelerations. So this is the typical phase space from a recent study, a yield study from Lammers and Wynn earlier this year. The number of planets with precisions on their orbits less than 20% is about 7,500. And there will be many more, or at least a comparable number of longer-term accelerations. This could also be combined in principle with Hipparcos, and as has been done with current data releases, to span a longer baseline than just the Gaia mission, which was about 2014 to just about a year or so ago. And then data release 5 should get to even lower masses. So when you think data release 4, think about 1 to 7 AU and masses down to about 1 Jupiter mass. Many of these are expected to be imageable. There should be lots of new, exciting trends, accelerations, curvature, and even closed orbits that are accessible with facilities like JWST. So I'm not going to go into this in detail because of the time, but Hipparcos can be combined with Gaia DR2 and Gaia DR3. This has been done by folks like Tim Brandt, Pierre Crivella, and others. William Thompson has a new one that's incorporated into a really fast orbit-fitting code. And there's a few papers in the series that are released and that are upcoming that incorporate all of these. OK, so we're starting to do this now. In my mind, this has been the single most revolutionary direction that has impacted high contrast imaging, probably in the past decade or so. The yields from blind direct imaging surveys are low. We get great statistics from that. But if you want to move beyond statistics at a precision of 1 or 3 or 0.5 or 7%, and you really want to go after the planets and characterize their orbits and their atmospheres and obliquities, you need to find them. And so this is, I think, the best approach that's been taken so far and has yielded this treasure trove of brown dwarfs and many giant planets. This is incomplete, as of even a few years ago. But you can also measure the masses of these planets and test models. There's a wealth of information that unfolds from there. So Gaia DR4 is going to fill in this cold Jupiter demographic census. We can start to probe things like occurrence as a function of stellar mass or metallicity or age, eccentricities over time. When do giant planets take on this broadening of eccentricities, assuming that they form in a circular orbit like we see from ALMA kinds of images and from the solar system. And then I just want to end here with a note about the connection to small planets. So, hopefully in a matter of years, I don't know how many years is, but some number of years into the future, we will all have the Habitable Worlds Observatory to look forward to. And so if we have, for example, an exo-Earth and a Jupiter analog and a sub-Neptune, we want to be able to see systems like this with orbital motion and reflected light and seasonal variations and all sorts of exciting things on these planets. But what we have to contend with is the possibility that there could be another planet in the habitable zone of these stars. I didn't even mention life, right? We could find life with these in principle, metabolic byproducts of life. But it's important to map out what is known about these nearby sun-like stars. So there's been lists of promising stars that might be ultimately target lists for HWO. And so I have a student, Katie Painter, who's been thinking about, in connection with comparable programs with radial velocities, using astrometry to map out what's known and actually what's not known. So the lack of a signal also provides information about what's not there. Because if you have a giant planet at 1 AU, of course, you're not going to be stable to smaller planets. And so just to get a sense of what was yielded from this kind of search for the 164 stars that have been released for community vetting purposes, basically to identify the best ones, about a third are accelerating. And many of these are consistent with known white dwarfs, binary stars, giant planets. But about 17, at least in this sample, have an unknown origin, and there's significant acceleration. So it just speaks to the level of work that I think we need to do as a community to find the giant planets and lower mass planets in these nearby, in the solar neighborhood, these nearby sun-like stars. OK, so I'll end here with some takeaway points. Giant planet architectures and demographics are really this patchwork of distinct stellar and planetary parameters. Circumplanetary accretion disks are beginning to tell us, I think, the outline of a story of when giant planets form, and at least some properties of their disks and how they might evolve. Giant planets peak. They appear to peak between this 1 to 10 AU range and are dynamically hot at older ages. So something is stirring up these planets over time. Spin-orbit alignments. Alignment seems to be the theme, although about a third of systems experience misalignment. And Gaia is going to deliver thousands of planets. So get ready to see lots of papers on arXiv related to Gaia DR4. Thanks.
Thank you. Questions in the room?
Thank you very much. Amazing talk. I have a question regarding the mass accretion rates of the planet. I was wondering, how do those compare to the accretion rates of planetary mass objects that are isolated?
Yeah, that's a great question. So the numbers are comparable. So we're not seeing, for instance, that the free-floating planetary mass objects are orders of magnitude or even an order of magnitude different. I think there hasn't been a clean census taken comparing these two camps. That would be very interesting to do. But any systematic biases that apply to one will apply to the other in the same way. So it's actually quite probably interesting to compare the two on an equal playing field. So as far as I know, they seem to be kind of comparable. And I haven't also seen a census of, there are many more of these free-floating accreting planets. It'd be interesting to assemble them into bins as a function of age and look at the accretion dissipation timescale, for instance. Compare that to the accretion dissipation timescale or bound companions. Yeah.
So for objects like AS209, how can you be certain that the AB is just due to the material in the CO gap and not a consequence of the material behind or in front of AS209?
Yeah, great question. I wasn't involved in that study. I think what they did, if I remember correctly from the paper, is, yes, if you just do it at a single epoch, you don't know what the extinction is to the distant 1 kiloparsec object or wherever it is outside of the disk. But with proper motion of the star, you can look at differential extinction. And I believe that was the strategy they took there. That's the first kind of paper. Maybe are you on the paper?
I'm on the
yes,
paper.
Tell us about it.
I mean, we went back to like 2005, big most data. There's even 98 data with this that we put in the paper that Gabriel is writing a follow-up, and that's exactly that. It's a differential extinction. It's like, okay, the first time we saw that, we thought, what's going on? The delta magnitude changed by a factor of like 2 magnitudes. It's like, our pipeline is wrong. And then eventually you work out it's behind the disk and the extinction changes.
And I see this as the beginning of that enterprise. You know, I don't know if this has been done before. I don't remember any papers of the sort. But if one could assemble a large sample, it would be very interesting to start to look at extinction or optical depth, you know, for lots of objects within gaps, outside of these gap structures.
The interpretation about like what's really causing a differential extinction, that's still up to debate. I mean, we'll put some explanation, but it could be something else.
Yeah. You choose.
I do have a question. So to go back to the accreting protoplanets, you have 6 of them. It's not the biggest sample. Is Gaia going to help us?
Yeah.
Yeah?
I think so. So Gaia is already starting to, I believe. So I mentioned this work of William Thompson and collaborators, and there are ways to assess using astrometric excess noise and RUI, differential Gaia DR2 and DR3 proper motions to already start to probe interesting spatial scales. There are a few papers from a few groups that are looking at transition disks and have identified signals that appear to be real. And these are kind of, everything is calibrated. Known giant planets from the NASA Exoplanet Archive are recovered using this methodology, and it pins down the mass and the separation exactly from the astrometric signature without the individual epochs right now. So there are, we're on to something. And I think that with DR4, there will be a lot of exciting opportunities for young stars, and not just at 150 parsecs, but the young moving groups and things like that. Yeah.
Okay.
So what are your hypotheses in terms of the giant planets that are becoming more and more dynamically hot over time?
Ask a theorist. I don't. Yeah. I mean, the obvious thing in my mind is interactions with another object in the system, so another planet-planet scattering of some sort. And we don't know. Maybe planets come in multiples, right? Maybe there's kind of a peas in the pod like architecture, which is this correlation of small planets in similar sizes close in from like Kepler-like planets. Maybe there's something similar for giant planets. It hasn't really been quantified. The incidence, not just of planet occurrence, but of multiplicity as a function of stellar host mass and stuff. And maybe they like to form together. And if they do, then maybe they, like in the solar system, they like to interact. And they're a little dynamically heated in the solar system, but it's also very easy to get more dynamically disturbed and not get damped down. And so perhaps that's what we're seeing. Maybe the solar system is in some sense a little unique. We're kind of long-term stable, but maybe these instabilities happen regularly, and that could be what we're seeing, this heated eccentricity. So it'd be very interesting to look at obliquity and eccentricity and those kinds of correlations at the sweet spot of giant planet location, at this kind of 1 to 10 AU separation. So this is kind of a big advertisement for DR4 exploration. And there's so much work to be done. Nobody quite knows how it's going to play out. And so I encourage everybody to enter into it. There's a lot of follow-up effort that needs to happen. Yeah.
My question, Kevin.
Oh, okay. Sorry. So should I interpret the result that spin orbit alignment is the theme for everything protoplanetary disk forward, that the cause of spin orbit alignment must therefore predate the protoplanetary disk phase?
I don't know. We're seeing it at least at that scale. It'd be very interesting if one could, and I don't know how you might get at this, maybe from like ALMA observations of class 0 protostars or something to try to get, assess the net angular momentum of a collapsing core or a real protostar, and then the natal envelope surrounding it. It'd be really interesting if there were differences there. But that's as far back as we can go right now. With a larger sample, one could slice and dice that sample, right? So look at 0 to 2, 2 to 4, 4 to 8. But there's also such diversity that I think that you'd need a large sample probably to pull out signal there if there's any evolution there within that time span.
I mean, there are some efforts along this, but I would love to chat with you later about it.
Yeah.
All right, guys, it's after the hour, so let's give Brendan one more minute.
There's still one more slot for dinner with Brendan, so please email me like you play it.